Uh, thank to the organizers for this invitation, and particularly for Louis Chen that for his encouragement for this many work in this line. My first exposure to star method was 1986. At the end of 1986, when Kai Chen gave me a paper. That's something related to star. I had no idea what it was, so I read about it. That's all my exposure of Stan's method until around 2013, 2014. This paper by Ita Gervich. Now is my colleague at Cornell Tech, and he essentially rediscovered the Stan method through in the queuing context. Okay. So now in retrospect, I will talk more about this connection with other work. So today I'm going to talk about this work, and has been collaborating with a number of people and more people. Now, particularly, we are currently working with Zhu Song is one of them that been actively working on some problems. So my talk is as you recognize, a lot of things are speculation. Okay, so speculation. So I have a lot of unanswered questions. Okay, so today I'm going to focus on three queuing models. Okay, focus on three queuing models, and the first one model, so-called LNC models, we have more sort of results are more complete. Okay, so that give you illustration that might be possible, some results, okay? So the key thing here is that the one key message I want to promote is that using so-called state-dependent diffusion coefficient to approximate these queuing systems, okay? Now, in the last 50 years, in my abstract said the last 50 years, research community has essentially been using constant diffusion coefficient. Okay, so that's pretty much it. Now, in asymptotic, no difference. Okay, asymptotic, if you go to some limit, no difference. They have the same kind of limit. But the pre-limit final system, they can make big difference. And I hope I can illustrate that a bit later. So let me first focus on the first model, the queuing model, so-called MMN model or queues. And if you are not familiar with this, I will introduce here are the model. So they are N servers, identical servers, okay, working in parallel. And there's a common waiting area here. If all servers are busy, then you're waiting in this common buffer, okay? And the arrival process Poisson and the parameter lambda. And here is a parameter service rate, exponential service time, there's mu, and also a parameter number of servers. So there are only three parameters: arrival rate, number of servers, and service rate. Now, the asymptotics, the community, the operational research community has been focusing on is the large lambda, right? That's very typical if you accompany growth from small size to large size, and a lambda increases. Whereas number of server here, mu is fixed, particularly if human beings are involved, right? You cannot speed up much, okay? What you can add a number of servers, okay? Add a number of servers. So that's the model here. So that's also, this M is a MMN model, and this is also known as LNC model. So this one is modeled by Markov chain, and just keeping track state is the number for customer in system at time t. The total number of customer in system. So those in service and plus those waiting, okay? So you just keeping track of the state. And you can very easily write down the transition rate diagram. And for example, here, if you're currently in state 2, the service rate is 2 times mu. And if you are in N plus 1 customer there, the service rate N times mu, because the total number of server you have N, okay, maximum, okay? And there's a one parameter or one quantity we keep often use is called R, is the overload. Is lambda divided by mu. So the 1 over mu is the average time each service required. So lambda is per minute, how many arrive. So this is how much work come into system per minute. And you should be, this one be less than n. Each server have 1 minute work for each minute. So you need, clearly you need this condition for system to be stable, okay? So if this is the condition satisfied, then this Markov chain has equilibrium, has station diffusion. And I'm going to use x infinite to denote this equilibrium. Sometimes I put parameter there, n, lambda, mu there. Often I do not, okay? And another quantity here is the so-called generator, right? This generator for this Markov chain, so the arrival from I current state to I plus 1, and arrival rate lambda, or current state is I, and if service completion, it's to state I minus 1, service completion rate is n times mu or I times mu, depending what state you are in, right? Okay, so that's the generator. So this is one slide on the diffusion process, right? Diffusion process has drift. B is I use B to denote drift, and sigma here the volatility coefficient. And so that's a generator for diffusion, okay, for this diffusion process, okay. So that's in the background, okay, the background. So the idea is that if given a Markov chain X and a diffusion process Y, okay, if these two generators are close, right, close, then their station diffusion should be close, okay, that's the idea. And indeed, there's for finite time, that indeed is the focus of E.C. and Kurt's book, right? Essentially, that's the book dealing with. So you have prelimit, convergent diffusion process, and if prelimit, of course, they're dealing with the prelimit is more than Markov process, okay? But essentially here is so you want this is very clear, intuitive, okay? Now, I want to say that here is that what is the limit here is a part of the issue here, okay? So often the most talk here is the limit is either normal or Poisson or something already identified, right? Here, part of the game is to identify what the limit should be, okay? What the limit should be. And so I consider that's the engineering part, engineering solution, okay? So now, of course, you star method is the mathematical framework to establish error bounds, okay, error bounds. And so I mentioned the Ita Govich paper a bit earlier, but if you trace back to really everything, most idea is here in this paper, right? And your Barber's paper, that's a generator method. So connection star method was generated, okay? It's there. It's just we were ignorant of that, okay? So that's I think this slides people already. So let me, I'm very clear here. In this talk, how the limit process, sometimes early slides are using Y. This is on this slide was Z. Z arises naturally from diffusion of mean field models. So now there's a very active group of people working on mean field models. Okay, that's the limit. Okay, and the challenge is one needs to. Okay, the nice thing is that this limit process, limit object is more flexible to be identified. But of course, there are new challenges. Now one needs to new gradient bounds instead of textbook results, right? If you have a normal Poisson, then textbook results already there. Now you have to sort of work out yourself, okay? So this thing, so it's not. So let me look at the generator. For this one generator, if I scale it, okay, often the scale parameter are using delta, 1 over square root of R. R is the overload. So I'm thinking of system like overload large, okay? Overload is large, system goes large. And so delta is small. And so you look, this Markov chain is going to be, you do scaled, it's going to be living on this grid, okay? And this is obviously just scaled Markov chain, that the generator. If you do the Taylor expansion, something will be clear, diffusion will emerge. But let me just establish some notation. First thing is this is so-called, sometimes I'm using this parameter regime. So R is the overload. I know my number server should be larger than overload, okay? How much larger? Well, it's beta times square root of R. There is one line work, okay? This is initiated by half an width, okay, water width. saying that the system can be run, if the system gets large, system can be very efficient. Very efficient in the sense that you can just fix beta. As system load is getting high, you just having this many servers, okay? And this will achieve both the both objective. One is a good quality service, meaning that waiting time is almost zero, okay? Second thing is a highly efficient, meaning all servers are almost 100% busy, okay? And that's not possible for small number of servers. You cannot achieve that. The two objectives are conflicting each other. But in the large-scale system, it's possible, okay? So this is often called, if parameter is in this regime, is often called half-width regime, okay? But I'm going to go beyond this, okay? But it's good to remember this, okay? And also another quantity I could define B, and particularly it's X and I is the integer state, right? And X, I'm going to use a scaled version of X. They are related this way. And then Bx is basically, it's partly linear and partly it's constant. Okay, that's Bx. That's the Bx. So now coming back to this operator, the generator, you do the Taylor expansion. You do the Taylor expansion, you got first order, second order, plus high order term. Okay, high order term. And this term, first order term, and this term is red one is called B of X. B of X, okay? So I'm going to use the notation B of X. So in front of first order here. Second order is actually state dependent, depending on state, okay? Depending on state. But as I said, the last 50 years, right, the diffusion approximation, this research community just use a constant diffusion coefficient. So if you have to use a constant, replace this by a constant, you probably wouldn't replace by any other constant except this 2 lambda. Let me explain what's going on, why 2 lambda, okay? So lambda is the arrival rate. What is this? This is a really departure rate. Departure rate depending on state. But if you want to use one number, the constant does not depend on state, then you probably want to use an equilibrium average departure rate. The average departure rate is going to be lambda also because the system has to work conserving, right, flow, right? Average departure rate has to be the average input rate. So you wouldn't put down any other number if you want to constant one, put this one. So that's that. And then I have this error term, second order derivative. There's still additional error term if I replace by constant and plus a higher error term, which is third order term, okay? So if I group this first line here, this is going to be my generator for the diffusion process. Okay, this is my generator. And then remember, this generator has constant diffusion coefficient mu. Okay, constant diffusion coefficient. And because it's delta squared times 2 lambda, that's going to be just mu. All right. So I'm going to, this object I'm going to focus on for the moment. That's the diffusion process. And this diffusion process is going to be sort of not quite mean reverting, because if you look at this drift here, if X is negative, then this one is going to be positive. We're pushing you up. But if X is positive, there's a negative drift, constant drift. So this one has equilibrium, this diffusion process. Okay, station distribution. And the station distribution of this one is going to be written, the density is this one here. Okay? So that's clear. I mean, now people are familiar with the density method, right? That's the density here. All right. So I am going to use the y infinite to denote having this distribution. Now the background is this y infinite station distribution for diffusion process. But actual mathematical proof, diffusion is irrelevant, right? You just, that's in the background, okay? So you don't need to prove that the diffusion process as a process exists or unique, etc. You don't need to. You just say y infinite has this distribution, right? That's the beauty of Stein's method, right? I don't have to look at diffusion process itself, okay? All right. So this is a type result you can get, okay, for this model. So now this is the Wasserstein distance, this is the Kolmogorov distance. And this constant certainly by no means is optimal, okay? One thing I want to mention here, this is the so-called, it's a universal approximation, okay? Universal in what sense? Remember earlier I introduced a beta there, okay, beta is there, square root staffing. In this theorem, nothing is assumed. Nothing is assumed. These three parameters, n, lambda, mu, they are arbitrary, okay, they're arbitrary. So they can go to heavy traffic or go to limit in arbitrary way, okay? I'm not particularly restricted to particular scaling, okay, but just scaling. So in particular system can be large, but it's not really particularly heavy traffic, but sometimes can be very critically loaded, okay? So system can be lightly loaded, critically loaded, and very heavily loaded. They all still true, okay? So that's this. And it's this, because this universal approximation here bounds, and that demands, that's more work, okay? Now let me just mention why it's more work. Is a typical term, error term is this one here. Actually, yesterday's talk, the main thing here coming out like, this is like, basically it's like linear. Absolute value of x, more like. X is the prelimit, right? Markov chain. Well, you want to estimate this kind of thing. And maybe the other way, okay? Currently, we estimate separately. You estimate this derivative bounds. These derivative bounds, depending location of x, state, it can be different, okay? For example, this one here is, when beta goes to zero, beta goes to zero meaning system very, very heavy traffic, okay, very heavy traffic. This one will blow up, right? This bound here, blow up. But hopefully that's unlikely state, right? That's unlikely state. So the total expected value can still be manageable, right? So, so that's give you illustration, and that's we need this kind of estimate we call moment estimates for the prelimit. Now it would be nice, like in yesterday's talk, that there's some people x cube or something here, that putting them together. I'm not sure. I'm intrigued by that. Some of the techniques there, whether they can be estimated together. But anyway, what we did is we did separately, okay? The gradient bounds separately and the moment bounds separately, okay? Putting them together, you got a universal approximation, all right? Now, that's actually not the focus of my talk, right? So, let's coming back to the Taylor expansion, okay? Coming back to Taylor expansion. Remember earlier that I have forced myself into the constant diffusion coefficient, mu. As a cost to that is I introduce additional error term, okay? That also involves second order derivative. So that's mu b of x. If you check on that, the additional error term is b of that. But why not putting them together? Why not choose diffusion coefficient that's not constant? Putting everything there in front second order derivative, that's your diffusion coefficient, right? So that's what I'm writing down here. And so from blue, I change it to new generator. Just combine this term, second order derivative into this term. So the mu plus the minus half delta b of x, that's called A, right? That's here, that's A. All right? This allows me to have a different diffusion process. Okay, I call it YH. So by changing previous mu here, this diffusion operator here, generator, now to this new operator here, generator, this A of x, I got a new diffusion process, YH. Is that clear? Previous Y, that's now YH, okay? And H hopefully stands for what? High order, okay? High order. So if I'm using this one, then epsilon is the same as this high order one. That is a third derivative, okay? It's here. All right. So now if this is a Stern operator, okay, Stern operator, now you have a bit more work to do, okay? More work to do because depending on the state-dependent diffusion coefficient. But now their work also called the density method, right? So people have developed gradient bounds on that so now I'm going to use a new density. So this is called YH infinite, having this density now. That's clear here, this new density function. And my color code here is green is for high order. Okay, so now let's see some some plot here. This is for 25 servers, okay? 25 servers. And so there are three curves. One is exact. Another one is use the constant diffusion coefficient. This is the total number scaled, total number of customer in system, okay? Scaled. And then you look at high order one and the exact one, you really cannot tell the difference, okay? You cannot tell the difference. So this is not quite in the limit yet, okay? So the load is, what's the load? Okay, 20 here, okay? All right, and this is for 5 servers, okay? 5 servers, and is the constant diffusion one is you see the noticeable it's off, okay? So the message here suggests that it's already the picture shows that the high order one is much more robust. Robust in the sense it cover more parameter region, okay? The accuracy. So indeed, this actually this is the one happy case that you have a mathematical result, okay, to justify that. And this is previously is the Wasserstand distance is 1 over square root r. Now it's W2. Under W2, it's 1 over r. Okay, the rate is 1 order higher. Okay. All right. Now, yes. Yes, discrete. Continuous. How do I make the pivot? I use this one here. Yeah. Okay. Okay. Good. Okay. All right. And this paper when we talked to Peter Glynn, so the end journals of probability, the major criticism is this model, the station distribution for this object is computable. Numerically, you can compute easily, birth-state process. All right? Why do you bother using any approximation? Fair enough, okay? Fair enough. And that was the major reason that the delay of publication. This paper has been on archive for a long time, okay? So now, in 2015, the STAN workshop here, Louis Chen, Adrian, you organized that one, and both Anton Braverman and I attended this one. And I remember the talk by Chi Man, okay? Moderate deviation, okay? Moderate deviation. Then immediately that I want to try this method on this one. So, and I happily joined on this one here. So let me tell that, okay, so this result here, the moderate deviation result. The important thing here, okay, so C is the universal constant, okay, universal constant. And maybe this one is the best understood in the setting of a Hagen-Root regime. Beta is fixed, okay? But the important thing here is this one here, this holds for all Z. Z all the way. I illustrate this on the right tail, okay? Didn't bother with the left tail for the moment, okay? So Z can go all the way to infinite, and when Z is large, this one is bounded. Eventually, we're not depending on Z, okay? We're not depending on Z. Okay, that's high order approximation, okay? Now, if you look at, indeed, the first one that shall help us to get is this one here, okay? If this is the previous, let's say, classical approximation, diffusion approximation, you get this kind of a moderate deviation result, okay, moderate deviation result. So it's 1 plus Z and a Z something. Now, of course, these are mathematical results, okay? You want to know, are these really tight, right? Are these tight? So I hope the following picture actually shows you that, give you some clue here. So there's a green one here, is a tail, is a flat, okay? Okay, now why tail is important, I think I don't need to get into that, particularly in operation research, that's related to service level, 5% service level, 1% service level. That's very important, okay? Service level that for customer, you need to promise something, right? So, so the tail, the moderate deviation is very relevant, okay? Very relevant. And you see clearly the difference, okay? The clear difference. And so the picture at least shows that, not mathematically, picture shows that kind of rate is optimal, okay, what you proved. So that's pretty much I have for this first model, okay? So let me move on to the second model. Now, then it's a lot of speculation going on, okay? So that's, okay. So this is a GIGI1Q, so, or sometimes GG1Q. This is maybe the simplest model, but it has very long history, okay? And also we connect some of it, so maybe connect with David Sigman's work on the crossing, boundary crossing kind of problem, okay? Hopefully it will be. So let me talk about this one here. So I'm looking at so this is one server, okay? So look at the waiting time. N customers waiting time equal to previous customer waiting time plus service time of N's customer and minus N plus 1's interarrival times, okay? If this one is positive, that's exactly the waiting time for the next customer, N plus 1 customer. If this is negative, the customer, N plus 1 customer do not wait at all, so it's 0, so that's plus here, okay? So the traffic intensity we assume to be less than 1, okay, less than 1, and this is so-called load factor. Interpretation of a rho is the utilization of the server, okay? So again, the heavy traffic meaning rho goes to 1, right? Heavy traffic, 100% server will be 100% busy. Of course, in that case is that when rho approaches to 1, the waiting time will grow to infinite as well, okay? So for fixed rho, this one has a limiting distribution, W, okay? So W is the equilibrium quantity that we're focusing on. This random variable. So the heavy traffic result is very classical. Kingman using some sort of Laplace transform, okay, to prove heavy traffic convergence. So this W depending on rho, okay, depending on rho. When rho goes to 1, it approach to exponential random variable, okay, exponential random variable. So the constant actually can be computed explicitly. All right. So that's the results in distribution. So okay, now this in terms of rate convergence, okay, in Stein's method, this is one attempt, but it's this result. This is in the general arrival process, okay, general arrival process. For Poisson arrival process, it's 1 minus rho convergence rate is clear, okay. This paper has that, and the other work has established that, okay, when the so-called MG1, okay, Poisson arrival process. This one result here, I want to put on here, so it's a result, but it's not quite satisfactory in the following sense. This quantity eta and y1 in terms of called ladder height, okay, because there's a representation W has the following representation. Sn is a random walk, okay, random walk. And this representation is give you this one. So this y is not the sort of in terms of primitive, okay, the input mod, the primitive of the model, okay, so that's that. And also it's unclear here, eta and rho didn't really explore here. What so far that as far as I know that we have a private notes to prove that it's like say the convergence rate in the general distribution case is the square root of 1 minus rho, okay, square root of that, or less than 1, okay, it's 1 minus epsilon at a high, if you by assuming high enough moments, okay. So now let me see that I want to propose something different, okay. So instead of constant diffusion, exponential distribution as a limit, I want to use this diffusion coefficient. This is a drift, this diffusion coefficient, and everything in terms of x is a primitive random variable, v is a service time distribution, u is the interarrival time distribution, okay? So this one here. And why we get that? I think I don't have time to, because what time do I have? Okay, good. So let me talk a little bit here. That's more than I thought. So this equation that prelimit, okay, prelimit operator, because we have the Lindley equation, remember that? We take n to infinite, you naturally got equation in distribution, right? So this often we call it for every macroprocess equilibrium distribution, it satisfies this something what we call the basic adjoint relationship. Equilibrium has to, for any macroprocess, satisfy equation, okay? So this equation characterize the state distribution. From here, I can do Taylor expansion. Do Taylor expansion, naturally you got this one. This is my higher order diffusion operator plus this something else, okay? So if I use this is my diffusion operator, then this one minus this is going to be, this becomes the error term, okay? This is going to be error term. All right, so here is what we have, okay, for this high order one. High order, instead for classical is the exponential. Kingman one is the exponential distribution, okay? Exponential distribution. So this is the density function we defined earlier, density function, okay? And you can get this kind of band, okay? This band, it's a fair amount of work, 1 minus rho. But I'm disappointed by this, right? Certainly it's not high order. I was expecting something high order, 1 minus rho, okay? Square or something, 1 minus rho square. So this theorem does not justify the term high order, okay? Does not justify that. And indeed, we realize it's not true in decay, Coulomb distance. You don't expect high order convergence, okay? You don't expect in Wasserstein distance and not even true in dW2, okay? This because the first moment we don't have the high order. But this may be there, let's see, okay? So for that, I want to explore what's going on I want to numerically try to explore what's going on the truth. So we choose a U has heavy tail density, okay? This heavy tail distribution, use the interarrival time distribution. And service time is constant, okay? Constant. So that's a model. And I want to play with this one here. And so here there are 3 curves, okay? So one is the exact, okay? Exact one, this blue one, exact. And exponential, this one here, green one. And the red one is a high order approximation. You see match a lot better, okay? That's the distribution. So if you see this kind of curve, you back for a justification, right? A justification. You back for mathematical results, okay? And this is talking about third moment. If I do the third moment, and forget about this last third curve, this error in terms of exact value, and if you use a high order one, the error is almost 0. If as the load goes to, as this load, okay? So it's a heavily loaded or underloaded. This is equally good, seems like using the high order approximation. But if you use the Kingman's one, then this here, the light loaded, particular error is much more significant, okay? All right, this is related to the what? Moderate deviation, okay, moderate deviation. And you see this, again, this result is this plot, okay, shows that if you use exponential approximation here, the classical one, you see this kind of growth, okay? Almost maybe linear, maybe quadratic, okay, linear. But if you use the high order one, it's quite flat here, okay? All right. Now, we don't have any results here, mathematical results, okay? That's just a plot. So it's right? So the relevant one for system, we sometimes talk about application. Application is that rho is not going to go to infinite or go to 1, right? It's 90% loaded or 80% loaded or 95% loaded. Under this kind of situation, what kind of mathematical theorem can you have, right? And so I think this picture is quite telling, right? So maybe it's because even if low is 90%, here is 90%, maybe Z is outside big enough, you have mathematical results there, right? So it's a mathematical theorem. This one, you hope that The model deviation, in other words, may be able to justify that. Now, the more interesting is that can the methodology be sharp enough to tell the difference, right? To prove this. So far, it appears to be difficult. It's not easy. Okay, it's because this is pushing the limit of the framework. Okay, so what's available. So that's that. So the last one I'm going to mention a few this model. Okay. Because it's the earliest one, the model that we focused on, okay? MPHN, okay? So this is the same as before, the model, okay? Except service time now have so-called phase time distribution. So why phase time? Well, sometimes job can be long service time. Sometimes can be short job, okay? Maybe a fraction of them. So this red one, for example, it's a long job, okay? The blue one here may be short jobs, okay? So with some probability. So phase time allow you to model, more realistically model service time distribution, okay? So I'm not going to get into too much of that. I'm just putting out this so-called Coxian distribution. Has two phases. Some customer need after service, the second service, stage service. Some customer, after service, leaves. So the variation is big for service time, right? Some customers long, some customers short, okay? So that's that. And so I'm not going to get into much details of diffusion approximation here. Suffice to say, the one diffusion approximation that indeed has been doing this in the research community for many, many years is using constant diffusion coefficient, okay? So another one is using the state-dependent diffusion coefficient. Now here are just two curves. Indeed, this case is that how many server? 1,000 server. If 1,000 server, doesn't matter. Doesn't matter which version approximation you use, okay? Because it's closer to the limit, it doesn't matter, okay? Doesn't matter. So I didn't even bother to plot the other one. Is that clear? Now, if here is a 20 server, now you see have three curves, the difference, okay? Three curves, the difference. So one of them exact, and another one is the traditional diffusion. That blue one is off, and then the high order one is on. Order is one on. And so the proof that mathematically so far what we have is to prove that blue curve is close to the exact one when system gets large, right? That's what we proved, okay? That was the one publishing Annals of Probability 2017, okay? 2017. So we have not been able to prove that these two curves indeed are close. We are not able to prove that. And maybe there's hope. I don't know. So let me state the results, okay? The 2017 paper. State result says that there's this convergence is 1 over square root r. That's not surprising. What limiting here is that I need to focus on the particular parameter regime. Rho, okay, in the half-width regime, right? So here it's not a universal approximation, okay? The result is not universal. Although I have believed it should be universal, right? Universal, but I wasn't being able to prove it. So that's that. And more recently, a colleague, some of you know him, Li-Hu Shi from McCall University, he told me now there is a proof, okay, for universal approximation. And the difficulty is, let me mention that here it's a multidimensional diffusion process, right? It's a limit process. It's not a multidimensional normal. It's not. But the diffusion process is a piecewise OU process, okay? Piecewise OU process. And so it has a station distribution. So in this case, Stein equation, you need to solving it's a PDE, okay? The multidimensional PDE. And in our paper, we use a classical PDE theory, okay, using PDE theory. And in order to get the universal approximation, remember that you need to estimate these parameters in different regions, okay, different regions and of these things. And the claim is that using the Malevin calculus, okay, Malevin calculus to prove this gradient bounds, okay, state-dependent gradient bounds. I'm very curious about reading the details about that, okay, so that is something, the progress going on there, all right. So let me end the talk, okay, summarize. So again, in our case, that the system prelimit is almost always a Markovian system. I didn't get into the state space collapse, okay, today. That actually is an important element in the diffusion approximation. Indeed, the most useful part, most powerful part of diffusion approximation is that in many parameter regions, the system from large dimensional system can be collapsed to low dimensional system. A good example is called join the short queue. If there are many servers, each one has a separate queue, you join short queue, okay? In this case, you expect queue size, different queue, a similar size, okay? That's collapsed to, say, one dimensional, okay? So I didn't get into that, but our paper dealing with the 2017 paper also dealing with another dimension is the state space collapse, okay? So Taylor expansion is a good way to discover an engineering solution, okay? Which target, limiting random variable you want to use, okay? That's that. And the main message here is that we should use a state-dependent diffusion coefficient, not constant one, okay, for robustness, for more robust approximation in different parameter regions, okay? So here I just list a few papers just in different community from here, but it's all related using star method, okay? So some are using diffusion approximations, some using mean field approximation, okay? So I stop here. Right. What's stopping it? What's the because it's an elliptic ODE PDE operator was the quadratic term. That thing is a positive definite, but depending on state. And there's not enough theory for us to quote. Right. Okay, I didn't put on here that hitting time. Right, I didn't put it. So you have generally you have a probabilistic representation of the solution to the Stein equation. I mean, no problem there. The estimate. The question is how do the coupling to get or stopping time to get the gradient bounds. I guess we are not good enough good at this to make it work. Okay, so right. So getting the gradient bounds, that's the bottleneck there. In the one-dimensional case, one can brute force to get a solution, right? To work out the gradient bounds, but in the high dimensional case, right, there probably is no other, I don't know if there's no other way or whatever, yeah, you're right, likely, okay, need to use diffusion, yeah. But so far in our 2007 paper, we didn't. No, not true. We did use Lyapunov diffusion. That diffusion, half-fast diffusion converged to equilibrium is used to construct because the PD theory only gives you certain amount stuff. You still need to have a probabilistic estimate. Yeah.